Hello, everyone. My name's Dingding Lu. I am a product manager at Microsoft. Welcome to Posette 2026. Today, I'm going to bring you a talk called Why We Built Azure HorizonDB. If you are a developer or a DBA and wondering what additional benefit Azure HorizonDB may bring to you, this is the talk you want to join. Great. Now let's take a deep look at why we built Azure HorizonDB for Postgres. Microsoft already has a Postgres service called Azure Database for Postgres that has GA'd around 5 years ago. It is a very popular database service and is used by many big customers we have, such as OpenAI. So, why we build another Postgres database? With experience running Azure Database for Postgres over the past several years, we observed that our customers want to have consistent performance or predictable latency when their traffic suddenly spikes to achieve cost efficiency, to scale out their workload when they need it, and to have minimum downtime. All this motivates us to look into how we can modify Postgres to run better on Azure and at the same time, modify Azure to run better with Postgres, such that we can build a new Postgres database, Azure HorizonDB, that can deliver all those customer asks. So if you put those two databases side by side, Azure Database for Postgres basically takes the open source Postgres, and we probably made roughly around like 20-ish changes to Postgres and hosted it in Azure VMs. So if you're looking for managed open source Postgres, this is one for you. Azure HorizonDB uses a different design and architecture to make Azure and Postgres work better together, but it is still 99.9% Postgres. We put a lot of effort to be very surgical when modifying Postgres to build HorizonDB. So if you're looking for tier one availability, performance, and scalability, Azure HorizonDB is a good option for all that. Plus, it gives you enterprise grade security and offers a rich set of integration into Azure Dev ecosystem. We have VS Code extension offering AI assisted experience via Copilot to have it in database AI experience. It also offers integration with Fabric with zero ETL data replication to Fabric One Lake so that you can do near real time analytics. Now, let's take a look at HorizonDB architecture. HorizonDB is built on the concept of database as logs and separation of compute and storage, which allows compute and storage to scale independently. From bottom up, first layer is Azure Blob Storage that keeps all transaction logs and data pages. So this is the system record for your data, and it is zone resilience by default. You don't need to do anything to make it more resilient. On top of that, we built two fleets. One is the shared wall storage to store the transaction logs. Another is the shared data storage for Postgres data pages. So shared means here all compute node can access both the wall storage and the data storage fleet. For the compute layer, a Horizon DB cluster supports one primary with a read-write endpoint and up to 15 readable HA replicas that form an automatically load balanced readable with a read-only endpoint. The primary and replicas are stateless, meaning we can lose all of this without losing your data, since data is stored in the storage layer and not in the compute node. The only data in the compute node is the SSD cache that basically is the caching layer we provide to gain performance boost. So because of the separation of compute and storage, it allows us to bring down a lot of resource-heavy Postgres background process, such as checkpoint or page writes to storage layer. By doing so, those processes will no longer compete against your real workloads for resources such as disk I/O and network I/O. So one thing before we move on, I'd like to point out is that we built the entire storage layer and some of the Postgres extensions use Rust. So Rust is a relatively new system language that probably around 10 years old compared to C language, which is created in the 1970s. So Rust is well known for support memory safety, concurrency without data races. While C or C++ is very hard to avoid memory corruption or buffer overflows, there is a big push in Azure to build a database or performance critical services in Rust. So we kind of already a step ahead to be future proofing by building HorizonDB using Rust. So now we have covered the surface of the overviews and let's dig a little bit deeper into the details. First, let's look at the shared wall storage and what benefits it brings. On the left side is the classic configuration of a Postgres with the HA setup with one primary and one standby. Logs are synchronously replicated from the primary to the standby with log shipping. So in order to commit a transaction, there are four serialized steps that Postgres need to go through. Step one, write the log to the primary local disk. Step two, send the log to the secondary. Step three, the secondary writes the log to its local disk. Step four, the secondary acknowledges back to the primary. So all those four steps build up into the transaction commit latency. Also, it is common to use network attached disks nowadays. So then you have to add additional network hops to the latency too. HorizonDB on the right-hand side uses shear log wall storage. That is zone resilience by default. We only need to commit the log by doing one hop across three availability zones. The standby doesn't need to interact with the primary at all. It can just get the log directly from the shared wall storage. This is very efficient when you have many replicas. Each replica is independent on its own. It doesn't need to talk to the primary or reconnect to the primary when the primary changes during failover. With this design, we get performance benefit with less hops to commit a transaction, also more reliability with decoupling the primary and the replicas. So why we build this whole shared wall storage service on our own? Why not just use an existing managed disk? So what we want is to only store like the tail of logs, the hot logs, which are typically small in size. And then we offload other cold logs to cheaper storage, such as your blob storage. We also need zone redundancy, low latency, and cost efficiency. Um, on the other hand, we also want to build this wall storage service as a generic service that can potentially be reused by other Azure services. With all those requirements, we don't see a managed disk will work for us. For example, Azure Ultra Disk does offer low latency, but it's not zone redundant. And with the 4 GB minimum size it requires, that can be quite expensive for our purposes. So having set all those requirements, we purposely built wall storage that is optimized for append-only writes and low and predictable write latency, and only frequently reads a log near the tail, and we are able to archive older walls to the blob storage. So now having introduced the shared wall storage service, let's put the pieces together and take a look at the life cycle of a write and how redo and update page works. So far we haven't talked about the shared data storage tree. So unlike logs that are small in sizes, data size can be very big and can't fit all in a disk. So that's why we shard the data across multiple nodes of the data storage tree. So when a write transaction comes to the primary, The log is persisted in the shared wall storage and the transactions are committed. The wall filtering service sitting between the wall storage and the data storage takes the transaction log streams, opens up the header, look at what pages this log is going to update, and send this log only to the shard that has the page to be updated. This is way more efficient than every data storage shard fetches all logs over the network, then probably throw away 99% of logs that are not relevant to the pages on this particular shards. So with the shared wall storage and data storage, and having wall filtering happening in the storage layer other than on the primary, all these transaction commit, log hardening, log redo, replica reads, data from the shared data storage, wall storage, archive walls to the Azure blob storage, all those processes are async process. Postgres doesn't need to coordinate any steps or wait for certain steps to finish. So another benefit from the shared wall and shared data storage design is failover. Before we look into how failover works for HorizonDB, let's just provide some context on how open source Postgres failover works. So failover, first step, it detects the primary, it failed if the heartbeat are missed. And then leader election done based on some consensus protocol configured with Petroni or something similar. And then they elect a standby and promote it to be the new primary, right? So all these steps can be done quickly, but the problem comes in when the old primary come back again and wants to rejoin. The old primary has its own copy of logs in its local disk, and very likely the log have diverged. So in order to fix this, Postgres need to run rewind. This is an actual step to take when the primary had a clean shutdown. The worst case is primary did not have a clean shutdown. And remember that the primary has its own local disk, has its own data. What if all the data is lost? Postgres needs to reinitialize with snapshots. With all these actual steps, failback is harder and can be error pruning. Also, the time between failover and failback can be long. So with HorizonDB, shared architecture, the primary and standby nodes are stateless and do not maintain its own copy of either the logs or data. So the first three steps of detecting failure with the primary, elect standby, and promote standby to be the new primary are same to the open source Postgres. The differences is when the old primary rejoins back, since it doesn't have its own local copy of data, it just directly reads from the shared wall storage. There's no rewind or reinitializing using a snapshot is needed. Thus, your failover fallback is much faster and reliable, and the window of the downtime is small. So we have seen how writes work with HorizonDB. Let's look at how reads work with HorizonDB. So in every Horizon node, whether it's the primary or replica, it has a local SSD cache that is NVMe disk. It's a fast disk. So when your read requires a data set that can fit in the SSD cache, we're talking about microsecond latency. Only when your read query needs more data that can fit in the SSD cache, it will talk to the shared data storage through a get page API call to get the page it needs. The latency is still within several milliseconds. So now you have a choice. So if most of your read query only need to operate on a small set of data and that data can fit in the SSD cache, you can have cold data sitting in a cheaper storage such as Azure Blob Storage. However, if the working set of data is larger than the SSD cache you can fit, you can choose to upgrade your compute size with a larger size of SSD cache to get the optimized performance. So we have covered the wall storage and how write and read transactions work. Now let's look at how we store data pages. So HorizonDB doesn't change the Postgres logical view of the data pages. To Postgres, it is still think that it talks to our 1 GB segment files. Under the cover, we shard the files and put them on our data storage fleet and on the durable Azure blobs storage eventually. So basically, the data storage free is a cache on top of the Azure blob storage, and it has ability to run reduce. So to provide resilience, the data storage free replicates copies of each shard across availability zones. So this way, it also reduces the tail latency when the compute node can now request a copy of a page from the shard that's in the same zone as the compute to reduce the latency. So let's talk about efficient data storage. So if a database has, that used attached disk as storage, then you need to pre-provision a storage size just in case, you will need all these spaces when your data grows. And then when the disk size does not fit your data size, you have to manually change to either larger or smaller later on. With HorizonDB, you don't need to do any of those because HorizonDB is designed to automatically grow or shrink with your data. HorizonDB shards data. This is all because HorizonDB shards data very efficiently. When the data grows and need to add another shard, we just run consistent hashing to find a block and bulk read the data into the blob because Azure page blobs are updatable. So you can just insert data into it. So another benefit of using Azure Blob Storage is fast point-in-time restore. Azure Blob Storage also supports snapshots that works the same as just snapshots. So this is very nice. So this basically make our life much easier to support point-in-time restore. All we need to do is to take a list of incremental snapshots, pick one to restore based on the point in time that you want, and redo some logs to bring to the consistent state at that point of time. So by now, we have covered HorizonDB architecture with separating compute and storage, why we purposely built our wall storage, and the benefit of us using the Azure Blob Storage. And if you're interested in more about Azure HorizonDB, um, you're welcome to check out the link below called Azure HorizonDB. And thank you for attending Posette, and thank you for attending this session.